We've covered alpha decay, where typically a heavy nucleus will turn into another heavy nucleus and produce an alpha particle, which is a helium-4 nucleus. And the helium-4 nucleus flies off, leaving the major nucleus there. So that's a conversion of, say, uranium into thorium, as we saw in the previous example. And then we saw, among lighter nuclei, typically, and intermediate-sized nuclei, you get beta decay, which is where you have a nucleus with a certain number of nucleons. It becomes another nucleus with the same number of nucleons, like carbon-14 becoming nitrogen-14. They both have 14 particles, but then producing an electron and an antineutrino in the case of negative beta decay, or producing a positron and a neutrino in the case of positive beta decay. All right, so in both those cases, alpha and beta decay, you started with one nucleus and it became another, and produced some other particles along the way. Gamma decay is a little different. It still produces an extra particle. Okay, in this case, a gamma particle, but the nucleus itself undergoes a different kind of change. To introduce gamma decay to you, I want to start with a beta decay. Boron 12. Okay, and typically stable boron is boron 10. Okay, boron 10, 5 protons, 5 neutrons. Boron 12 is unstable, and I don't know what the half-life is here, but it becomes, okay, this is boron 12, 5, because all boron has 5 protons. It'll become carbon 12. Let's see, this is going to be a neutron becoming a proton, so it's going to produce an electron and an antineutrino. This is negative beta decay. Okay, so this is, in other words, to introduce gamma decay, I'm taking you back to beta decay. Okay, this looks fine, and it is fine, except for one thing. This carbon 12 is not normal carbon 12. Okay, its difference, whatever that difference is, which I'll say in a minute, is indicated with an asterisk right there. Now what that means is this. Do you remember back last week we were talking about hydrogen? It had its ground state, right? When the electron was in the lowest n equals 1 state, we called that the ground state. And that's the state that the atom likes to be in. But there are also excited states, n equals 2, n equals 3, n equals 4, all the way up. So that the atom could exist, the electron, well, the atom really could exist in all kinds of different electronic states, right? So there was the ground state, and then there were excited states. And when the electron in a hydrogen atom falls from an excited state down into a lower state, could be the ground state or another, but when it falls back down to the ground state, what does it emit? It emits light. Some of that light's infrared, some's UV, and some is visible light. When the atom falls from a high state to a low state, it emits light. Okay? So an atom can be in the ground state or an excited state, and when it goes from the high state, the excited states to the ground state, it emits light. Well, it turns out, believe it or not, nuclei also have energy levels themselves. Forget about the electrons. The carbon-12 nucleus can be in different states. It has a ground state, but it also has a large number of excited states. And this star you see indicates that when boron 12 becomes carbon 12 through negative beta decay, okay, right? This is beta decay. Make sure this is clear in your notes. Beta, negative beta decay. When boron 12 becomes carbon 12 through this negative beta decay process, the carbon 12 is initially not in its ground state. It's in an excited state. The nucleus itself is in an excited state. That's what the star means. Okay. What happens to that carbon 12 now? It goes from carbon 12 in an excited state. Again, star means excited state. It undergoes gamma decay after the beta decay. Okay? Carbon 12 goes to carbon 12 in its ground state plus light. Okay? Just like when the atom, the hydrogen atom, went from a excited state to its ground state, it emits light, including that spectrum of hydrogen that we saw last week with the 4 colors in it. It emits light. Some visible, some ultraviolet, some infrared. So does an excited nucleus. When it decays to its ground state, it emits light. A gamma particle is simply light, but it is a gamma ray on the high end of the electromagnetic spectrum. Okay, that's why they're called gamma particles, because they were first discovered in radioactive decay. That's why they're called gamma rays up there. So this light has energy. It has high energy. Instead of EVs, a half an EV, a fourth an EV, 2 EV, whatever, that you get from an electron in an atom, this has energy up in the MeV range. They are gamma rays. Now it turns out that gamma is the symbol for photons, light particles in general, but that gamma came from the fact that we had alpha, beta, and gamma decay. So this light that gets emitted by this nucleus is very energetic and not good for us. Okay, there are gamma rays around. That potassium 40 in the walls, it produces gamma rays when it decays. Okay. But the gamma decay itself, this is the gamma decay. Woo, this sound. How about that? That is the gamma decay. This is beta decay. Just set up the gamma decay. Typically, something needs to happen to put a nucleus in an excited state. Oftentimes, that's another kind of radioactive decay. It's not easy just to get a nucleus into its excited state. You got to really whap it hard to make that happen. But nuclei in excited states is a normal product of beta and alpha decay. So this is the actual gamma decay itself. So in general, the gamma decay in general is X, A, Z star to X, A, Z plus gamma. That's the general expression for gamma decay. And this happens exceedingly rapidly. Okay, there's only a few cases we know of where it really takes a while. So we usually don't talk about half-lives so much when it comes to gamma decay. Okay. There are things called metastable states of atoms and of nuclei, but for the most part we don't talk about half-lives for gamma decay, not typically. But that's what gamma decay looks like. Okay, so an alpha particle is a helium nucleus, a beta particle is an electron or a positron depending, and then a gamma particle is just a photon. All right, that's gamma decay. Next up, an example.